Hey everybody, welcome to this week's edition of video notes for Mr. Flugum's AP Chemistry class. That's right, these notes are for AP Chem. So thanks for tuning in, you guys. And these video notes will be due on Wednesday this week. That would be September 19th. Okay, is when these are due, and I'll be checking for them. We're going to start talking about light and atoms and a little bit of quantum theory. Doesn't that sound fun, you guys? Well, let's get started. Alright folks, so what is light? Well, light is a form of energy. Is it a wave or a particle? And the answer to that question is this, right? It is both. Sometimes light has characteristics that make it seem like a wave. Sometimes it has characteristics that make it seem like a particle. Just so you know and remember, a particle of light is called a photon, right? Now, when light acts like a wave, we have to look at it in a certain way with certain characteristics. So, when it's a wave, we have things like the wavelength. As a wavelength, and so lambda is the Greek letter there, is the symbol for wavelength. We also have something when we have a wave that is called frequency. This is all stuff that you learned in Gen Chem last year. Frequency is the number of wavelengths per second. Okay? So, those are two really important characteristics of a wave, right? The wavelength here, the lambda, and the frequency of wavelengths per second. Okay? Frequency, which is the number of wavelengths per second. Excuse me. Here's a look at frequency, right? Here's a low frequency wave right here. And if you notice with the low frequency wave, we have very few wavelengths, right? If we look at a high frequency wave, right here, we have lots of wavelengths. That means this, right? That the wavelengths are much shorter as the frequency increases. So when frequency goes up, the wavelength goes down, right? If you look here, here's a funky thing to notice. Frequency, the symbol is a kind of a V there. And that'll pop up here just down the road in a few slides. So when we think about light, sometimes we just think about the light that we can see. But there's lots of other forms of light and energy. They all act in a similar way. They all are like particles or waves, right? They all have wavelength and frequency. And we start down here. These are gamma rays. Okay, those are radioactive waves, right? And we work our way through X-rays, ultraviolet, visible light, right? Infrared, microwaves, and radio waves. In the middle here is visible light, right? And as you can see, right, violet or purple has the shortest wavelength. Okay, red has the longest wavelength. Okay, so and this is a continuous spectrum, right, as things fade from one into another. Alright, so here's a formula that we're going to use. This formula is provided for you along with the constants on the handout that you will get with your test. Alright, here we have c, which is the speed of light, right, 3 times 10 to the 8th meters per second. Okay, wavelength, which needs to be in meters if we're going to use that speed of light, and the frequency v, right? By the way, frequency, you guys, is measured in hertz. Okay? Now, the wavelengths units that we have for much of the light wavelengths that we're going to work with are nanometers. So it's important for us to remember this, that 1 meter is 10 to the 9th nanometers. So that means this, right? We need to do some converting with our wavelength before we can use it in this formula. Because our speed of light is 3 times 10 to the 8th meters per second. So here's a little practice problem for us, right? Find the frequency of green light that has a wavelength of 545 nanometers. Now we're going to use that formula from the last slide, right? C equals lambda V. Okay? And we're also going to do this, folks. We are going to need to change these nanometers into meters, so that we can actually use this formula with the speed of light that we have been given. Okay, now I want you to do this. I want you to pause the video for a minute or two while you see if you can work this out, and we will talk about the answer when you get back to class on Wednesday. Thanks a lot. Okay, so here's the deal. I want you to think of the Bohr model, right? And according to this model, which is supported by ionization energy data and stuff like that, right, that we talked about, every electron has what's called a ground state. This is where the electron stays most of the time. Okay, spends most of its time there. Now, if you notice from this, right, there is no in-between level. So if an electron is here at level 1, it either stays at level 1 or it has to go up to level 2 or level 3. There's no level 1.5, right? There's no level 1 3/4. It's kind of like an elevator in a building, right? If you get on a certain floor, you either have to go up a floor or down a floor, or down 5 floors, or up 5 floors. There's no in-betweens, right? My point being this, that sometimes electrons absorb energy. Say when a certain frequency of light hits them, or when electricity is put into the system and into that atom, the electrons might absorb that energy and get excited, right? So when an electron absorbs energy, it increases levels, right? So it does this, right? It increases levels right here. It gets excited. So it might go from level 1 all the way up to level 3 because it absorbed a bunch of energy. Now, when the electron returns to its ground state, that energy is released in the form of light. Okay? So, my point being this, right? Remember, when that electron increases levels, it has to go whole levels. There is no steps in between. So you might be saying, Mr. Flugum, what are you talking about? Here's what I'm talking about. I'm talking about quantum theory and a guy named Max Planck. Okay? He had a hypothesis that energy only gets radiated, okay, in discrete units or packets, right? So packets of energy called quanta. Okay? And you can't have half a quanta or a part of a quanta. You have to have a whole quanta. So we used to kind of assume or think this, right? That energy would come out in a constant line, right? That depends on how much energy is going into it. It's how much energy we will get out, right? And as intensity increased, we'd get more energy put out, right? Well, we've actually found that that is incorrect. Energy actually increases in discrete units, right? Called quanta, right? It either increases by a full step or a full packet or quantum of energy, or it doesn't increase at all. Now this is supported by the Bohr model, right? Quanta, right, are due to the energy levels shown in the Bohr model, right? So remember, if we have an electron here, it can only go up to level 2 or level 3 or level 4. It can't go anywhere in between those levels. And each level represents a quantum of energy, right? And that is why energy gets released from things in packets or quantums, right, as steps instead of a continuous release of energy because of these energy levels. Now, not to be outdone, our friend Max Planck came up with an equation, okay? Came up with energy, right, is equal to Planck's constant, which is here, and will be given to you. You don't have to memorize that, times the frequency, okay? So we can figure out how much energy is being released per quantum in joules using this equation. So here's a little practice problem for us, right? How much energy is transferred in a quantum of green light that has a wavelength of 545 nanometers? So I want you to think back to that problem we did a few slides ago, right? You probably found out what the frequency of that light is. Now you can just do this, right? Take your energy and multiply it times Planck's constant and the frequency. And that will tell you how much energy is being released per quantum. Well, we'll check that also when you get back to class. And I hope you guys have a great day. Bye-bye.